All right, so welcome back. So here we're talking about 4.3, the properties of our logarithms. And again, as explored before, the idea of a logarithm is the inverse operation of the exponential. Noticing that we have this idea log base b of x equals y is true if and only if we switch to the x and y's, which is what's happening with an inverse function to begin with. B to the y equals x is the same thing as log base b of x equals y. So they give us log base 3 of 27 equals y. The base stays the same, so base of log, base of exponential is the same number. It's the switching of the other two things in the problem there. So that's why it's 3 to the y equals 27. The 27 and y swap locations. So we can use this to evaluate each of these problems. Because if this is the idea of log base 4 of 64 is equal to x, they're really asking 4 to what power gets us 64? And that's 3. So if we kind of just separate this out here so I've got some clear room with where everything is going, we're getting 3 for A. For B, we are recognizing that, again, that's equal to x, so 8 to the x equals 2. 8 is really 2 cubed, so it's really 2 to the 3x equals 2 to the first. So that means x is really a 1/3. If we have log base 3 of 1/9, again, 3 to the x equals 1/9. A fraction implies a negative exponent, so since 9 is 3 squared, 1/9 is 3 to the negative 2, so that x value is negative 2. Same thing's going to happen here. We have 1/5 to the power of x equals 25. So that's really 5 to the negative x then, and then 5 squared, which is going to get us x to be a negative 2. All right, so anytime we're dealing with a fraction, we're generally going to be having a negative. If both the base and the number are fractions, then we're probably not going to have a negative then, we'll have a positive, but generally that's where the fraction comes in. Now, a nice little thing, if we have 1, no matter what the base is, the answer is always going to be 0, because this is saying 5 to the x equals 1, the only time that occurs is if the exponent is 0. And then these last two right here are does not exist. It's undefined. Either one you want to go with there. Does not exist, undefined. I would accept either way because we can't evaluate that. 7 to the x equals 0 is not possible. If x is incredibly tiny, like 7 to the negative billionth power, for all practical purposes, it's 0, but it's technically not 0. It's really like 0 point and a whole ton of zeros before you get to a number there. Whereas something like this one right here, 1/3 to the power of x equals negative 9, that's not possible. The only way to get a negative number using exponents is if it's a negative base raised to a power. And for these logs, part of the rule is the base will never be negative. All right, so when you're evaluating these things, you're just writing it as the base raised to the power of x equals the number you want to work with, and it's got to work out in some nice way. Now, a couple different types of logs, because you'll see on your graphing calculators that there is a log button on there. So the one that just says log is what's called a common log. It's log base 10. So they'll never write the base there. They'll just say log x. So you'll know that if there is no little number in the subscript position in between the g and the x or whatever's there, it's log base 10. Whereas a natural base is base e. And this is a special number. E is the value of 2.71828, and it kind of keeps on going on forever because it's irrational without repeating. E comes about when we start talking about the idea of limits and calculus for a certain type of rational function, evaluating it as it goes on forever. That's where E is coming from. So if we have a log base E, it's a special type of log. It's what's called a natural log. And it's written a little bit differently. We don't write it as log base E of x, or as ln of x for a natural log. And we can use both common logs and natural logs to evaluate logs of any base. Because most calculators can't do, for example, log base 3 of 7. That's not an exact value that you can do, because 3 raised to a power does not get a 7 nicely. There'd be a decimal there. Newer calculators, like the newer TI-84 plus CE, and even some of the older 84s can do a change of base formula in there. It's got a function if you go into math and scroll over to you scroll down to math and it says log base. You can do it in there. But if you have an 83, you have an older 84 that doesn't have this ability, or it's a scientific calculator, the only way to do log base 3 of 7 is with this change of base formula, where I'd rewrite this as log 7 divided by log 3, or ln 7 over ln 3. Log of the number divided by log of the base, or ln of the number divided by ln of the base. You can use either one, it's not going to really matter. I'll use them interchangeably, just kind of depends on the scenario. So like for here, for example, 7 to a power does not get us 295 nicely, so we'll say it's log 295 divided by log 7. And if we do that, log 295 divided by log 7, make sure you're careful with your parentheses. The calculator will give you a set of parentheses to type it in, close it off before you hit division. You should get 2.923 because we're going to the thousandths place. All right, so make sure you're getting that when you're using your change of base formula. Now, different properties of log, so we have your three main properties. So this allows us to rewrite log expressions. So product, if we're multiplying two things on the inside, they can get their own individual logs by adding in between them. Whereas where for dividing two things on the inside, they can get their own separate logs by subtracting them. And if we have an expression, something being raised to a power, the power becomes the coefficient in front of the whole thing and there is no more exponents. And this ability to rewrite these log expressions will be very useful for solving equations and very useful for stuff like derivatives next year in your calculus class. So the idea here is before we start anything, we want to rewrite everything in terms of an exponent. So if there are radicals, we got to recognize that's really x to the 1/3 power. This is y to the 1/2 power. And then we rewrite this for every single component, the 2, the x, the 5, and the y all get their own log. If there's a coefficient in front of it, that's because of an exponent. So like x would have a 1/3 coefficient, y would have a 1/2 coefficient. And whether it's a plus or a minus in front of the whole thing is depending upon the location. So the 2 and the x are both in the numerator, so they're both positive. So I don't need to write anything in front of the log 2, but I'll write a plus 1/3 log x there. The 5 and the y came from the denominator, so they're both minus signs. And that's our fully expanded version. The idea is each individual component gets its own log, and there cannot be an exponent in there. There can't still be products. There still can't be quotients. They have to all be an individual component. Whereas condensing reverses that, where we recognize something like this right here, log x over 2 is really 1/2 log x. So depending upon how it's written, they'll either write as a 1/3 like they had there for the y, or they'll write it as a over 2, so it's really the same thing as a half. So the idea here is this log, so the x has got a coefficient of 1/2, so the exponent is 1/2. The y is a coefficient of 1/3, so it's a 1/3. And z and w are both negatives, so it goes on the bottom with the coefficient being the exponent there, z squared and w cubed. We can then rewrite that if they wanted us to as the square root of x cube root of y over that z squared and w cubed. Either way, perfectly fine, no matter how you want to write that answer. All right, so that's the idea behind the expanding and condensing. It's all a matter of just giving individual logs when you're trying to expand it out, or put it as a single log when you're trying to condense it down. This also only works if they're all the same base. So if we had log base 10, log base 10, log base 10, then log base 4, couldn't condense the log base 4, only the log base 10s. And again, positive coefficients go to the numerator, negative coefficients go to the denominator. It's very straightforward. All right, so next up, we're going to talk about graphing these log functions, and then we'll get into the idea of solving exponentials and log equations. So I'll see you next time for those videos.